In this video, I'm just going to run through a couple of the textbook questions from RLT3. I'm going to kick off with, in Chapter 10b, Question 3, we are asked, how many ways can 5 books be arranged on a shelf? And the key word here in this question is arranged. So because we're finding arrangements, remember that the word arranged is the same as the word permutation. So there's a couple of ways we can approach this. We can think about the permutation formula, which is NPR is equal to n factorial divided by n minus r factorial. And remembering that what this formula means is if you have n objects, so in this case 5, if you have n objects and you're selecting r of them, this is the formula that gives you how many arrangements you can have. So one way to think about it is, okay, we've got 5 books and we are selecting 5 of them. So it's actually 5p5. So let's see what happens here. So we get, sorry, not n. So n is 5 and r is 5. So we have 5 factorial over 5 minus 5 factorial. Let's, knowing BODMAS, do our brackets first. So we get 5 factorial divided by 5 minus 5, obviously 0. 0 factorial. Now, from one of the YouTube videos that we watched, 0 factorial we know equals 1. So this is just 5 factorial over 1. When you have something divided by 1, it's just that number. So it equals 5 factorial, which should be 120, I think. Yep. So there are 120 ways that we can arrange these 5 books on a shelf. The other way you can approach this question is just think about what you're actually doing. So imagine you've got your 5 books, and it can help to draw it out, especially when the number is small like 5. So imagine you got your 5 books and you want to put them on a shelf. When you go to grab your first book, you have 5 options. So your first step is you have 5 options. Once you've chosen your first book, you now have 4 books to choose from. So this is like our multiplication rule. So you begin with 5 choices, then you have 4, then you have 3 to choose from, then you have 2, and finally, when you get to the last book, you've only got 1 option. So 5 times 4 times 3 times 2 times 1, that's 5 factorial. Because remember, a factorial, when you have, say, 5 factorial, you're just multiplying all the numbers less than 5 together. And that equals 120. So 2 different ways to approach this question. I'm going to skip to question 11 here. Find the number of 4-letter code words that can be made from the word complex. Part A of this question is if no letter can be used more than once. So what we're doing here is we have 1, 2, 3, 4, 5, 6, 7. We have 7 letters to choose from, and we're finding the number of permutations when we are selecting 4 of them. So we're finding, we've got 7 letters to choose from, we're choosing 4, and we're finding arrangements, so permutations. 7p4. Let's plug this into our formula. So 7 factorial divided by 7 minus 4 factorial. Doing the brackets first, we get 7 factorial over 3 factorial. 7 minus 4 is 3. And let's use our calculator for that one. That gives us 840. So there are 840 different ways that we can arrange 4 letters from the word complex. Part B of this question asks if the letters can be reused. Now, in this situation, it's different from permutations, so we can't use this formula. The reason for that is, let's write the word complex. And let's do an example. So let's say our first letter, so we're going to choose a 4-letter word. And I'm going to write down in these boxes the number of options I have for each letter. So when I'm choosing my first letter, let's say it's an M. And I had 7 different options to choose from. Now, because the letters can be reused, I don't need to cross off the M. So in this box, I'm not going to have 6 options. I've actually still got 7 different options. So I could use M again. And I had 7 options. When I choose my third letter, I've still got 7 options. Maybe it's a P. I had 7 options for that one. And finally, the last one, maybe I choose X. And again, I had 7 different letters I could have chosen from. So I had 7 options 4 different times. So using the multiplication rule, it's 7 times 7 times 7 times 7. And that turns out to be 7 to the power of 4, because reminding ourselves that when you have a number to the power of something, you're multiplying it by itself that many times. So let's use our calculator to find where are we? Seven to the power of 4 is 2,401. So there are 2,401 ways that we can arrange a 4-letter word from the word complex if the letters can be reused. Question 14 from chapter 10b. If no digit can be used more than once, find how many numbers that can be formed from the digits 3, 4, 5, 6, and 7 that are A, 2 or 3 digit numbers. So a key word in this question is or. Now, remembering from the chapter 10a and 10b PowerPoint, often when we see the word or, that indicates that we're going to need to use the addition rule. So if we're choosing 2 or 3 digit numbers, what we want to do is we want to find how many permutations will give you 2 numbers, and then we want to add the number of permutations that give 3 digit numbers. So we're going to have to find each one individually and then add them together. So I'm going to start by finding 2-digit numbers to start with. So we're going to use our permutation formula. We have got 1, 2, 3, 4, 5. We've got 5 digits to choose from, and we're finding permutations when we're choosing 2 of those numbers. So 5 digits to choose from in total, and we're choosing 2, and we're finding the number of arrangements. So it's 5p2. Let's put this into our formula. 5 factorial over 5 minus 2 factorial. Doing the brackets first, we get 5 factorial over 3 factorial. 20. So there's 20 different ways we can make 2-digit numbers. Now let's look at 3 digits. This is going to be the same sort of logic. So we've got 5 digits to choose from, and we're choosing 3 in total. So we end up with 5 factorial over 2 factorial, which gives us 60. So there are 60 different ways we can make 3-digit numbers. Now the question asks for 2 or 3 digits. So for 2 digits, we've got 20 options. And for 3 digits, we have 60. So if we want 2 or 3, we add them together and we get 80. Part B of this question asks us to find how many permutations are there if there are 3-digit numbers and they're even. So the logic behind this question is a little different to what we've done so far. Let's do a similar technique we've done a few times where we sort of draw the boxes for the 3 numbers. So I think this is going to help us understand what's going on. So if it's going to be an even number, we know that this third digit has to be even. So we ask ourselves, out of the numbers we've got to choose from, how many are even? We've got 2. So there's 2 different options that we have for this last digit. So in here, I'm writing the number of options we have. So we can see that there's 2 different options. Another way to sort of work out how many options are for this last digit is you can use the permutation formula, but it's probably more simple just to simply observe there's 2 options. But if you did want to use the formula, the way to think about it is you have 2 even numbers to choose from, and you're finding the number of ways you can arrange those 2 even numbers, and you're selecting one. So see how if we're just focusing on this last digit, we've got 2 even numbers to choose from, and we're choosing one of them. So 2p1. In the formula, this should end up just being 2. And we have 2 factorial over 1 factorial is 2. So we get the same answer there. So what we've done is we found out we've got 2 options for our last digit. Now let's focus on these 2 digits. So what we've got here is, let's say our third digit is already chosen. So either 4 or 6 has already been chosen. That leaves us with 1, 2, 3, and either one of these. So there's 4 digits left to choose. So we have 4 digits to choose from, and we're arranging them by choosing 2 of them. So that's how we sort of work out the number of arrangements for the first 2 digits. You have 4 digits to choose from, and you're choosing 2. So there are 12 different options. Now another key word in this question is and. So remember back to our 10A and 10B PowerPoint, often when you see the word and is when you're going to use the multiplication rule. And we're going to do the same thing here. So we found the number of permutations when we're choosing an even number is 2, and the number of permutations for the first 2 digits is 12. So in total, we're going to have 12 times 2. We're multiplying these 2 numbers together, and that gives us 24. So there's 24 different arrangements where we can have a 3-digit number and it's even. And part C of this question, we've got how many permutations occur when the number's greater than 7,000. And we've got the 5 digits available up the top here. So let's use some problem solving skills and break down what is the question actually asking when it says a number greater than 7,000. So what we really want is the first digit needs to be a 7 or higher. And in this case, we've only got the highest digit is a 7. So it's got to... Actually, this will be a couple more steps than I first thought. So greater than 7,000 means we can have a 4-digit or a 5-digit number. So if it's a 4-digit number, it's got to start with a 7. So that's our first one that we're going to find. So it's got to be a 4-digit number and starting with a 7, or any 5-digit number. Because we can see here, even if we have a 5-digit number that starts with a 3, it's going to be at least 30 something thousand. So it's going to be more than 7,000. So these is what we're going to ask ourselves. First, we're going to find the permutations for a 4-digit number and it starts with a 7. And then because of this key word that we're asking ourselves, or, we're going to use the addition rule. We're going to add the permutations for any 5-digit number. So let's focus on the first one. So if it's starting with a 7, remember we got a 4-digit number and it starts with a 7. So if this has to be a 7, there's only one option for that first digit. So you can imagine we've got 1, 2, 3, 4, 5 different numbers. So we've got one option for the first number. And then for our final 3 numbers, we have 5 digits to choose from. Sorry, no, because we've already chosen one, sorry. We have 4 digits to choose from, and we're choosing 3 of them. So for these final 3 digits, we're going to have 4p3 permutations. So in our formula, 4 factorial divided by 4 minus 3 factorial. 4 minus 3 is just 1. So 4 factorial over 1 factorial. We can put that in our calculator. 24. So for our first number, there was one option. And for our following 3 numbers, there were 24 options. So we use that multiplication rule. Obviously, 1 times 24 is just 24. So there are 24 different permutations for a 4-digit number, and it starts with 7. Now let's work out how many permutations for any 5-digit number. We have got 5 numbers to choose from, and we're choosing 5 of them. So we're just saying just how many arrangements, how many ways can we arrange these 5 different numbers? It's 5p5. So we've got 5 factorial all over 5 minus 5 factorial. That gives us 5 factorial over 0 factorial. Remember, 0 factorial is 1. 0 factorial is 1. So that simply gives us 5 factorial over 1, which is 5 factorial, which is 120. So, because we are asking ourselves 4-digit numbers and starting with 7, or any 5-digit number, we need to add these permutations together. So in total, there are 24 plus 120 options, 144 different ways we can arrange these digits into a number that's greater than 7,000. Moving on to 10C, we're going to look at question 5, which is how many netball teams can be chosen from 13 players? Now, obviously, because we're on chapter 10C, we know that the entire chapter 10C is on combinations. So this is probably going to be using combinations. But let's say we didn't know it was from chapter 10C. We just had this question in general. We have to decide, is it going to be a combination or a permutation? The way you want to think about it is, if you have... Oh, I haven't finished the question. How many netball teams of 7 people? So how many netball teams of 7 can be chosen from 13 players? So let's say the first 2 people you choose, let's say we've got Bob and Anne, and then 5 other players, okay? If you had have instead chosen Anne and then Bob, and then those same 5 other players, those 2 teams are the same. So in a permutation, choosing Bob first and then Anne would be different to Anne and then Bob, but not in a combination. So, because when we think of it like that, when you're sort of talking about choosing teams or choosing things where the order doesn't matter, remember combinations are when the order is not important, we're going to need a combination here. So our combination formula is NCR is n factorial all over, I think it is r factorial multiplied by n minus r factorial. So that's the formula we're going to need to use. So let's think about what is n and what is r in this situation. We have 13 players total to choose from. So 13 players to choose from, and we're finding the number of combinations when we're choosing 7 of them. So it's just going to be 13C7. So let's work this out. 13C7 is 13 factorial all over 7 factorial multiplied by 13 minus 7 factorial. Let's do our brackets first. 13 factorial all over 7 factorial times 13 minus 7 is 6, so 6 factorial. And now I'm going to use my calculator. You could use a calculator for this step. It doesn't really matter, just up to the personal choice, I guess. So it gives us 1,716 different ways you can choose a team of 7 people from 13 players. Question 12. In how many ways can a committee of 5 be chosen from 8 women and 4 men without restriction? So without restriction, we're not going to worry about who's a woman and who's a man. We've got 8 and 4, we've got 12 people in total. So what we're doing is we have 12 people and we're finding the number of combinations when we're choosing 5 of them. That's all. So remember, n is just the number of objects you have to choose from, and r is how many you're actually choosing. So 12C5. Let's put that in our formula. So 12 factorial all over 5 factorial times 12 minus 5 factorial. Now maybe I'll just put that entire thing in the calculator. So 792. So without restriction, there are 792 different committees of 5 that can be chosen from 12 people. And part B, I've just sort of condensed the question here to save myself having to write it. So again, we are forming a committee of 5 people from 8 women and 4 men. But for part B, we've got the restriction if there are exactly 3 women. So let's think about these 5 committee positions that need to be filled. We've got 5 different committee positions. 3 of them need to be women and 2 of them need to be men. So let's think, how many combinations are there that we can choose 3 women? So what we're asking ourselves is, we have 8 women in total to choose from, and we want to find the combinations when we're choosing 3 of them. So this 8C3 is going to tell us how many ways we can select 3 women from a total of 8. So let's work this out. 8C3, 8 factorial all over 3 factorial times 8 minus 3 factorial. $56. So there are 56 different combinations for choosing 3 women out of 8. Now for the next part, so for the men. So we have to fill the final 2 spots of men, and we've got 4 to choose from. So the number of ways we can choose 2 men from 4 is 4C2. 4C2, 4 factorial all over 2 factorial times 4 minus 2 factorial. Six. So there are 6 different ways we can choose 2 men out of 4. Now you may be wondering, how do we know whether we need to use the addition or the multiplication rule now that we've got these two numbers. The way to sort of think about it is, I like to use the tree diagrams analogy. So let's say if we've got 56 different ways, or maybe, yeah, we've got 56 different ways that we can choose the 3 women out of 8. So I'm not going to draw 56 branches, but imagine you've got, 56 different options in this sort of tree diagram. Then let's say you choose this first one. This first one gets chosen, and then on the end of this branch, after you've chosen your 3 women, there are 6 different ways to choose 2 men out of 4. So connected to each branch, there's going to be 6 more branches. So you've got 56 individual branches for your women, and on the end of those 56 branches, there's going to be 6 branches. So we have 56 groups of 6. So we're using the multiplication rule here. We start with 56 options, and then we have 6 more options after that. 56 times 6 is 336. So there are 336 different ways that you can choose a committee of 5 people from 8 women and 4 men, where there's exactly 3 of them. Last question we're going to discuss is question 16. Joanne is offered a selection of 5 different sweets. She can choose to pass or select any number of them. In total, how many choices does she have? So what we're saying here is, because she can pass or choose any number of them, she has the options. She can choose 0 out of the 7 sweets. She could choose just 1 out of 7. 2 out of 7, 3, 4, 5, 6, or 7. So she could choose, what am I talking about? There's only 5 sweets, not 6 or 7. She could choose 0, 1, 2, 3, 4, or 5 different sweets. So let's see how many combinations are available when she's choosing 0 sweets. So she's got 7 to choose from, and she's choosing none. So the number of combinations where she chooses 0 is going to be 7C0. Or, so we're using or. So remember, when you sort of ask yourself or, it's the addition rule. So we're going to add, how many combinations are there if she's only choosing 1? So out of the 7, I've done this again, 7. It's a 5. Why am I thinking 7? Out of the 5 sweets, she could choose 1. Or she could choose 2 out of the 5 sweets. Or 3. Or 4. Or 5. Now there is a shortcut rule when you have this. When you're adding all the combinations up from 0 all the way up to the number you want, so like 5 out of 5, the shortcut is, it just ends up being 2 to the power of the number of choices she has. So that's a bit of a shortcut. So she has 5 different sweets to choose from. So the shortcut is, it becomes 2 to the power of 5. To the power of 5 is 32. So there's 32 different ways, 32 different choices she has in total.